We're going to talk about kind of a specific way that I've been exploring to kind of escape flatland in Elixir. First off, this is a graph of kind of how I've been working on this project and this talk ahead of time. And so I'd like to thank everybody for being here and helping me terminate what's clearly an infinite loop. So this kind of story started back in 2019. LiveView had just been released. It was on GitHub. I was playing with it on the weekend. And I built a Kanban board. It was pretty simple. People were happy. I was demoing it. You know, you change the status and it moves a ticket over. And it was pretty exciting. But that was kind of too businessy and kind of boring. And I wanted to play with some natural language processing. And so I devised a project. It was basically a text box. You type into it, and it would calculate metrics. So the idea was, you just change text, and it would pipe through a whole bunch of functions. So I started with a module like this, really simple, just string and enum. And you can use it like this. You pipe it in a tokenize, you count words, you count uniques. And then you can, calculate some more metrics and some more first and last. But that wasn't really very satisfying. It was kind of too easy, and there were some issues. One is I wanted to change some of these metrics and these different parts of the pipeline at runtime. And two, a lot of these relied on common pieces. If I wanted to calculate all of these metrics for the same text at the same time, I'd have to run tokenize for every single metric, and that's kind of unnecessary work. And finally, this is Elixir, so it's like, how do I run this concurrently? And the solution I kind of fell towards was this, which is, this is a directed acyclic graph where we're modeling the dependencies between the steps. And in this model, there's concurrency between the independent steps. And this was pretty neat. But I kind of got distracted with this whole idea and this little natural language processing project in the first place. And I kind of ended up just yak shaving on this idea for about 2 years instead of actually working on this feature a lot. So, let's see. I should probably back up and explain, first off, like what's a DAG, what's a graph? And a graph, in this case, is not a chart, it's just circles and lines. We're drawing relationships between entities. DAGs are graphs where they have arrows. So we have a direction between the steps, between the nodes. And the acyclic part means there's no loopbacks. So our graph at the beginning of our endless procrastination loop, that was cyclic, and that's not okay in DAGs. And so the TLDR is DAGs are circles with arrows between them. And we're going to use those in Elixir. And data flow is just a DAG, except we're using the arrows to model the data flow between our steps. It's pretty easy to make a DAG in Elixir. We're going to use the libgraph library. There's also the digraph library that comes with OTP. And we're basically just adding edges between entities. And we can make this more interesting by taking functions and throwing our functions in the graph. It'll look something like this. And this is basically what our data flow graph is. We have functions, we have lambda functions, we have arrows, and they're modeling the flow. And so how do we evaluate this? And we evaluate this by pretty much just traveling over the graph and feeding inputs. So we're going to start at the root, we're going to travel over, we're going to map, we're going to build out these inputs, and we're going to continue downwards. So this would be the next layer. And if you're an Elixir developer, there should be something that stands out to you here, and that's this. Because anywhere there's something like this, it's embarrassingly parallel. And we're Elixirists, so we're going to slap async stream in there. And so it's really easy to do this. We just replace our map with some async stream. And we don't really have to use task async stream. We can use pretty much any implementation of a parallel map for a fan out. So we could use flow, we could use some sort of worker pool, we could use gen stage, whatever we want. And now, because our graph is just a data structure, if we want to add another step, we just add another edge. And so we go from here to here. And that's pretty neat because this is us changing our program at runtime. So there's three main takeaways. You use a directed acyclic graph. You have explicit parallelism. All you have to do is go from the top. Anytime the arrows go out to the children, each child is independent and can run concurrently. So it's a declarative parallelism. With our task async stream or that enum map, we can pretty much implement evaluation in any way we want. So we can execute it using, distribution, concurrency, in a single process, however we want to do it. And because the program is data, we can change the program at runtime. And this meets a lot of those goals of that original project. And this is the demo. You can go to the URL at the top if you can see that. Let's see if I can navigate to the browser. And so this is the feature. Let's see if we can zoom. And if we type nice things, we calculate metrics and they change. And you can see we've been executing about 318 steps so far. We've got a log of all the tasks that we've completed. And we can see over here we have the graph of our natural language processing steps. And if we type about things poorly, we'll see it flash. And because the graph is a JavaScript library, it still kind of struggles to keep up. And there's a queue in the background, so it just keeps going and going. And oh, they're finished. And then finally, because it's a graph, we can change these at runtime. So we can toggle off some section of our metrics. We go back to our graph. We can see there's less. Oh, internet connection. And we can go back and we can turn off some more. We see less nodes. And here we are with the rest of them. So that's pretty neat. We can build an application and we can surface this idea of transforming our program at runtime into the application. And so this is the fundamental idea behind most of these like serverless tools or no code or low code. Or data flow graphs are also how Microsoft Excel works under the hood, where you change something and then it goes through the dependencies of all the cells that's referencing it. So it's a pretty neat idea. Okay. But that's not enough. This book actually, I think, is the best description of all of the issues with scope creep and project management. But the idea is, if you give a dev a Lambda, they're going to want some other things. Like so far, we've just been piping in like deterministic transformations between steps. But we're programmers, and there's other things that we want, like rules, joins, and state. And the main thing about rules is their control flow. But they're also a good practical storage of knowledge. So you'll see these a lot in expert systems, rule engines, production rule systems. And the main idea is that you take an expert, they'll encode their expertise about a procedure, an issue, and you'll save all of these rules in a database that you'll retrieve later and evaluate at runtime. Common systems like this are like the Ops5, which is probably I want to say it's the original one from 4G. There's Prolog, which is kind of what we're doing, but backwards. And then there's REAT and LEAPS, which are like evaluation algorithms for rule-based expert systems. And the basic idea of a rule is that it has a left-hand side and a right-hand side, or a condition and a reaction. And the basic idea of that is just a function. So in a lot of ways, a function operates like a rule, where we are matching on the left-hand side, and if that matches, we can execute the right-hand side, in this case, 42. So we can expand this into two functions, one that returns a Boolean and one that returns the reaction. And so as a graph, it would just look something like this. And because it's a graph, we can start adding more rules at runtime and evaluate them as a composition. So in this case, if we feed it ham, we'll get a reaction that it is delicious, but the others won't. Okay. But then there's another caveat. In Elixir, we have things like guard clauses. And in this case, we could just break out our left-hand side as the full conditional. But the problem is, if we're evaluating this with a composition of many, many rules, and if this is like a situation where rule-based expert systems apply, which is like an airliner where they're trying not to make planes crash, you have thousands and thousands and hundreds of thousands of rules. And there's likely a lot of overlap in conditions. So the optimization strategy is that you want to avoid doing unnecessary work in this match phase. And so one way of doing that is to expand. And in this case, we're expanding our conditionals by pulling out every expression and making a separate function. And we can embed this in a graph something like this. So in this case, we have our first two conditions on our left-hand side that are bound by and, so we build a conjunction. And then we have our or, which is just a separate path to our right-hand side. And that's the basics of rules. And I'm not going to go too deep into joins. The only thing you really need to know is that joins, at least what I'm calling joins, are steps with more than one parent dependency. So in this case, step C shouldn't run until A and B. And then you can also model state machines. And I don't have a good implementation of this yet. That's something I'm working on. But I was thinking an API for modeling a state machine could look something like this, where we can have a reduction where we're matching on various states, and we can react based on our state. And this might look something like this. So it's just another way of expressing a program. We're decomposing functions, we're transforming them a little bit, we're embedding them in a graph, and that gives us different properties. Let's see. And that isn't without trade-offs. You can control the execution. Like we have lazy evaluation, we can return a set of things to do some work, but there's also overhead. You're now playing the part of the scheduler. And that can be good or bad because now you can choose how you want to execute your program, but maybe you don't. Maybe there are situations where you just want to do it. And also, the compiler can't save you. And I've definitely run into this debugging because you don't know you have a bug until you execute it. And it's in an async or something, so it can be tricky. Let's see. Finally, there's some links. I'm not sure if anybody can see this, to a couple notebooks. This first one is really just what we've gone over so far. And the second one is the library that I've been working on. And so let's go to the first one. Hopefully this works. There we go. And I'll share this out on Twitter or someplace. Let's see. And the main takeaway from this, once we get back past our review, how we're rendering graphs, how we're rendering steps, how we're evaluating. Let's see, changing DAG, joins, rules, expansion, state machines, is this. So in here is a module that describes roughly, it's basically, I heard Elixirists like pipelines, so what I did was I made a pipeline module so you can pipe while you pipe. And so this is basically a minimal version of what I described of how you can kind of encapsulate this idea of making step dependencies inside a module. And so this is what our little text processing pipeline might look like. And finally, there's the library I've been working on. First caveat, it barely works. Maybe I needed to be in that infinite loop a little bit longer. So like I can support rules and joins. I'm still working on state machines. And it's basically a high-level way of doing this from Elixir. So it's doing a lot of dangerous things like macros at runtime. It's definitely in make it work status. But it can do a lot of fun things like support a high level dependency graph as data. Here's our text processing pipeline. We're just modeling a tree here. It supports both eager and lazy evaluation. So, and the basics of lazy, in this case, is we're not returning a stream yet. We're just returning work that can be executed. It supports stateless rules, and it's currently expanding conditionals. So we have an intentionally convoluted function with guard clauses here, and it'll transform that into a graph that looks like this that we can evaluate. And like you can tell it's a work in progress because there's a bajillion inspect statements here. It supports captured functions and lists of functions. This is actually an example of one of the problems that I've been thinking about, which is identity of a function. A lot of these conditionals have different representations that are equivalent, or parts of a condition which might not be necessary to evaluate if some other part has been evaluated already. So this is kind of the limitations of the sort of heuristics that we can apply. And this will build a graph like that. Finally, there's composition of different things that can flow. So we have 2 rules in this case, and we can embed them inside of a workflow. And so this is that idea of grab all of the rules that you care about from a database, slap them in a graph, evaluate them together. And that's the basics of a forward chaining rule-based expert system. There's also protocols for how different pieces can be merged together. So in this case, we can take a rule, a variety of rules, and we can merge them together into a big workflow like this. Let's see. Finally, this is kind of a new thing that I had to do recently, which is I needed to be able to execute workflows in separate processes, or if it was distributed, and I needed to merge them together. And so what I ended up doing was use more graphs. In this case, this is an example of the memory structure, where what we're doing is we're drawing causal dependencies of what happened in the graph over time. So here we have a fact, and what we're doing is we're modeling relationships of what happened during the evaluation of these steps. And this has some advantages because graphs are very easily merged. So this is a match phase for many conditions. Let's see. So here you can see like we have satisfied conditions we're evaluating. Here's what happens when we get all the way past the left-hand side into the right-hand side where we've produced another fact. Let's see, there's some more notes. I'm just going to gloss over that. We're using a state monad. And here's the kind of the main thing. Here we're executing part of the workflow in 2 separate contexts. So this is the same workflow, 1 and 2, where we're executing different parts at different times. And so we have a memory structure here. It looks like this. And then we have our separate process that's executed somewhere like this. So we can see they have different histories across their execution. And all we have to do is just merge them back together. And this is a bit hand-wavy because what we've done is we've assumed that all of the steps that we've executed so far is deterministic. This doesn't work if you have side effects, because then you've executed the side effect twice in 2 different execution contexts. Let's go back to the slides. This is where you can find me on socials. Where's my hand wave guide? Oh, here it is. And so far what I've described is not really, to me it's not that interesting. Because all of this is stuff I wanted, and this is just like the road to there. I still need to figure out an API for how we specify what's deterministic and what's impure. Otherwise, we don't really have a good way of telling your evaluator when you need to introduce some amount of coordination or some sort of transactional guarantee. The big idea is it's like sending the program to the data. You can either build or compose or term to binary and code your graph, send it over the wire, execute it locally. And I'm not really sure where to go. I want to build more of these low-code systems. I want to do state machines. like these domain-driven design, CQRS, event source systems, they're just another flavor of state machine. And if you can express a state machine in a graph, why can't we build our domain-driven design constructs like aggregates and process managers at runtime? You know, why can't we do this in our application? Finally, there's more stuff about distributed systems that I'm going to hand wave away, which is problems of identity. Right now, we're just hashing functions, but that is not the best source of truth for an identity. We could also use AST, but then you have another function that might be expressed as a module function and an anonymous function. Maybe they're computationally equivalent, but the AST is slightly different. So if I'm trying to make sure I only run something once, I don't really have that guarantee with what I've got so far. Finally, there's a few more hand-wavy ideas about ways we can compose these things safely. One is using property-based tests and contracts for whether or not you can connect a step to another step. Joe Armstrong has a really good talk, I think it's from 2014, where he talks about connecting things together, where he introduces session types, and which is pretty much a state machine for describing the API contract of your system. And that's another area that I'd like to explore. Let's see, I've already glossed over this. And I think that's it.